Thank you for joining me for the next 40 minutes for the next upcoming talk, The Power of the Device Mapper from DM Cache to DM Zoned. I'm the last person between you and the lunch, so I'll try to stay in time to ensure that everybody gets lunch in the break. And so, my name is Werner Fischer. I'm from Austria, working for a German company called Thomas-Krenn, and I will, guide you through the upcoming nearly 40 minutes and give an overview about the device mapper. But first of all, before we start, some questions to you. I'll try to see hands in the slide, but I think I can do it. Who of you has ever used LVM? Okay, maybe easier question. Who of you has ever not used LVM? Okay, still a few, so 3 or 4, 5 people not using LVM yet, but most of them do. Who of you has used software RAID? Okay, same question again. Who of you has not used software RAID? Okay, a little bit more, so more LVM user than software RAID user. And now an interesting one. Who of you has dmsetup directly without invoking any? Okay, I'll see one hand over there, and okay, about 10 other hands here. So I roughly would say about 10% to 15% of the audience has used dmsetup. So that's good for me, so I have enough to tell, but also for the other ones, I think there's something in the talk here. And one important question this time, who of you has heard of the bike factor? Bike factor? We had an interesting talk yesterday from Hans de Goorde about creating a vibrant and healthy kernel community. And he told how much important it is to look also for the bus factor or track factor. And I got to know here in Amsterdam that it's also important to watch it for the bike factor. So take care when you're around here. The bikes are really getting fast here. And fortunately, thank you for the stool. I will use it a little bit. Because unforeseen things might happen, not only in the kernel development, like we had in the last talk, but also in real life. And so take care. And just as a hint, there's no speed limit currently on the bike lanes here in Amsterdam, so watch out, really. Okay, but now to the agenda. What will we go through in the upcoming time? First of all, I will give a short recapitulation of the storage stack and the virtual file system. So you see on the right-hand side how the storage stack is working, and I'll give you an overview of this. And now I'll then concentrate on the device mapper within the storage stack, how the device mapper framework works, and give a few simple examples how the dmsetup commands are used. Now at point 5 and 6, we focus on the targets for production use and for debugging use. So we have those two kinds of use cases for device mapper targets. And within those targets, I will give a short overview of all of them and grab into a few of them deeper, like the video target there. And as you see, this simple diagram, as it seems, isn't that simple maybe at all. So in case you want to look through it, you can grab a color print copy here in the front now at the end of the talk. Maybe otherwise easily go to this URL, alps.at/lssd, then you can follow the diagram through the talk too. Otherwise, just grab a copy after the talk. So, a short recapitulation of the storage stack and how is the virtual file system working. In Linux, this is a simplified overview of how the whole storage stack is working. We have all above the applications, the processes. When they want to access files, they can go to the virtual file system. And we see there are many different kinds of file systems in there. So not only the block-based file systems, which will be our focus right now, but also network file systems and other file systems like special file systems or pseudo file systems. And then we are going below down with block IOs, and this is the point where we can attach to the device mapper targets. And you can see we can stack them up together, go a little amount of rounds in there before we hit then the block layer and the multi-queue stuff and going down to the request-based drivers and the physical devices. So just to get an idea where the device mapper is located. Regarding the virtual file system, it's been around for a long while. By the mid-80s, it's been introduced with System 5, and it provides a generic interface to the applications. So the big advantage is operations like read, write, open, and stuff like that. They always work in the same way. It is regardless which file system is being used, regardless it's a block file system, a network file system, a special file system, everything is a file in Linux. And yeah, that's the situation here. So we can take advantage of this when going down the storage stack. And here's a more detailed view of this virtual file system. And you can see here we are in the block area because we want to watch out for the block IOs, and there are file systems like ext4, XFS, ButterFS, and stuff like that, where we go down there. And in addition, there are other file systems here too. At this point, I have to say that I'm not a kernel developer at all. I'm just a guy who wants to understand how things are working. And in case we get some deep questions, I've seen that there are some developers in here and maintainers, so thank you for being here. Yeah, in addition to the block way in the virtual file system locally on the system, we can also can get access over the network via the Linux I/O target or the NVMe target, for example, and get the block IOs in there and going down further the way in the storage stack. This is just a little more detailed diagram here. It's been updated today, so it's updated for the current kernel version 6.16 and added some new devices in there, like the set loop device or the NFS local I/O mode, which is now also in here. And yeah, this reflects the current stack as of the current Linux kernel. Let's take a look on the device mapper in the storage stack. As mentioned, it's just in the middle, in the heart of the storage stack, just before the block IOs go down into the block layer itself. And for those stacked block devices, the device mapper targets most often is used via tools like LVM. And as mentioned, there are targets for production use and targets for debugging use. In addition to the device mapper itself, this is the software rate. Other examples like the distributed replicated block device or bcache also behave in the same way that you can stack them over each other. So those are on top of normal block devices, and you can go as many rounds as you want and stack them one over each other. I've inserted this slide only that you have a list of all about 20 production use targets and the other debugging use targets here. An important information, though, because I mentioned the block layer and block MQ is that for stacked block devices, there's no block multi-queue and IO scheduling involved at all. So things that you can configure for physical devices can't be done here because it wouldn't make sense on those device mapper targets, and I just wanted to point this out with an example. Here we're having encrypted LVM volume group, just to have the contents of my laptop encrypted. You see it's done via dm-crypt in the background. And when I look down below and try to access the multi-queue subdirectory or look for schedulers, I see there is no subdirectory and there are no schedulers to choose from. These are things that are relevant for physical devices, so you have to go one layer down to set this up. There's no things involved in here. And for those of you who want more information about that, you can watch for the recording of the talk of last year when I went through this in more detail. So let's get further to the device mapper framework. The device mapper is used to map physical block devices to higher level virtual block devices. The primary goal is to create an abstraction layer and to be independent of the physical design below. And for that, it provides a mechanism to modify those BIOS structures that go down the storage stack and to modify them while being in transit, and then map them to block devices. And so that's a good layer of virtualization in here that makes it very flexible to use it for different things. To achieve those goals, there are some user space parts and some kernel space parts. And for the user space, it's a dmsetup command, which users rarely use directly, as you have seen already when I asked the question. It's really a low-level tool. So normally you're using tools like the LVM tools or MD tools or crypt setup or something like that, because then you are taking care of saving the metadata and issuing the right dmsetup commands and don't make any mistakes here. So dmsetup is mainly used for recovery purposes or also for using targets that don't have any other tool support like the LVM stuff has. When we look at the kernel side of the story, we are having the mapped devices. Those are logical devices provided by the different device mapper drivers. They usually exist in the dev mapper directory and are your gate upwards the stack, for example, to put file systems on it. In between, you have the mapping table, which describes how each range of logical sectors should be mapped down below to the physical devices, and below that, then the target devices. One important information here is that the device mapper is working at the sector level. So a sector is 512 bytes, and this is regardless of the physical geometry of the block device. So you always have to deal with 512 byte sectors here. So let's look for some commands, some example when you're using dmsetup directly, how is it used? There are different commands. The first important command is dmsetup create, where you can create a new device with a given device name, and to choose which target type of device you're creating, you're using the table option, where configure what target to use, which range you're using, and stuff like that. This depends from target to target how it is used. And yeah, if it's successful, you can get then a device in the dev mapper directory with a device name, and the syntax is mentioned below. I'll show an example for the linear target then too afterwards. Removes, on the other hand, removes a device. It cannot be removed when it's still in use. For that, there are two options. You can force it. This will replace the table with a new one, which fails all I/O. Or you can also remove a target deferred, which means the device will be removed when the last user closes it. So these two options are also possible here to remove a target. And as mentioned, normally you won't do this as a user, but it's good to know in the background how things are working there to get an idea how the device mapper is working there. One other interesting thing here is that you have also the ability to send messages to different targets. So depending on the targets, they support features to get some messages from you if you want to configure something or change something in the configuration. This depends really on the target itself. And the syntax is dmsetup message, then the device, sector, and the message. And if no sector information is necessary, the sector is simply 0. We will see an example with dmdust in the end to show where those messages are being used. Suspend is only for temporarily suspend. It stops any new I/O, flushes any existing I/O, postpones further I/O as long as the device is suspended. Syntax is the same, nearly the same, dmsetup suspend. And to get back, you can do a resume afterwards to unsuspend the device, and the postponed I/O gets requeued for processing just by using this dmsetup resume command. So let's look at those targets for production use. As mentioned, there are many of them. I'm not an expert on each of the 20 different targets but I want to give an overview. And as one of the most recent new targets which have been added, I think in kernel 6.9, I will provide a little bit deeper look at the video target, at the virtual data optimizer, because it's a thing which is not well known right now. Maybe a question, who of you knows the virtual device optimizer video already? Okay, 3 or 4, so that's a good topic. I think I will focus on that. So first of all, the most easiest target is the dm linear target. It maps a linear range of the device, mapper device, onto a linear range of another device. It is the basic building block for device map and logical volume managers. And as for all other targets, I'll show you through the talk. Every time I have a link into the documentation where I can get further information about that. Here I provide an example. I just set up 2 loop files here and have a simple command. Then below dmsetup create test dm linear, specifying the table with the starting point and the end point, the linear target. This linear mentions that it's the linear target using def loop as a backing device, starting from 0, and then I have my target here. So it's an easy syntax here. Next, target dm cache. There are different kinds of caching targets. This dm cache is one that tries to improve performance of a block device like a spindle by migrating some of its data to SSDs. This has been popular for a while before NVMe storage became cheaper and easier to adapt. Decision of what data to migrate is left to a plug-in policy module. And as again, also here, we are having more documentation here. I think I'll speed up a little bit to have the time to go into the details of the video more. dm-clone, next one produces a one-to-one copy of an existing read-only source device into a writable destination device. And the main use case is to clone a slow remote device into a local writable device with a low latency. So it redirects the reads and the writes accordingly, and you have the advantage when you have a slow remote target, for example, via a network or something like that. You can initially clone this and take full power of low latency when doing writes, and with the time you're getting all the data. And once you have everything here, you can remove it and replace it by a linear table, and then you have your local copy here. So as the name suggests, it's for cloning. Crypt, dm-crypt provides a transparent encryption using the kernel crypto API of block devices, also used by LVM, for example. Most of the time a user sets up a laptop, for example, it's used underneath without the user knowing it, but this is where the work gets done to ensure that the data is secure. Another target, emulate block size, EBS. It's very similar to the linear target, but it emulates a smaller block size when you're having a larger device, like a 4K native disk. This is helpful when you have, for example, applications or file systems that you want to have using 512 byte block sizes. You can do this with that target. Next one in alphabetical order is the era target, the period of time. Also again similar with the linear target, but it's tracking block changes within different points of times. And for that, it's also being used, for example, for monitoring changed blocks when you're using backup software. There's also another example here. I've put in further documentation to get more details on that. Integrity. This emulates a block device that adds additional per sector tags to store integrity information. Here one thing is important, that when you are adding integrity information, you have to ensure that both the sector and the integrity tag get written at the same time. So either both of them must be written or none of them must be written. It mustn't be the case that one is written and the other not. So to guarantee this, DM integrity uses a journal. This is more secure but a little bit slower, or a bitmap that's faster but less secure. And you can use this, for example, as a standalone target to detect silent data corruption on the disk or on the I/O path, a feature which is also available in some file systems, but in case you want to add it for a file system which doesn't support that, you can do so by using the DM integrity target. Mirror target mirrors data across two or more devices. I think I have to speed up a little bit. RAID provides a bridge from device mapper to software RAID, allows the drivers to be accessed using a device mapper interface. And before we get to video, we have a few ones left. Stripe, you can do a stripe across one or more underlying targets. And switch is one that is for special storage devices. So for example, some Dell EqualLogic or some other iSCSI storage arrays where you can add an arbitrary mapping of fixed size regions of an I/O across different paths. So for some storage devices. So you don't need to take care of that when you don't have these. Thin target provides thin provisioning, is mostly used by LVM, so you can take a look at the LVM documentation. And as we have had stripe, there's also an unstripe where you can do the other way around. You can unstripe stripe targets to access the underlying disks. And the good news here is that you can also use this to unstripe a hardware read 0. So when you have a hardware read 0 below and you want to access the disks individually, you can do so by using the dm unstripe target. This is also useful in some setups. And in the past, I'm not sure how it is nowadays, it was also possible to reduce the read latency for some special NVMe SSDs, which have multiple cores in themselves because they have some mapping which core is responsible for which areas. So there's some more information on the documentation at the kernel, docs.kernel.org site. So I think it's one before we get into the video. Yeah, it's still one, the last one before video, it's the DM Verity. This provides a transparent integrity checking. It's read-only and set up most of the time for a verified boot path. And yeah, you can also get more information on there. And now I think I have enough time left to show you the main new thing, the virtual data optimizer. And I think this is one that has often been overlooked and not thought of, especially in enterprise environments. It's really a very powerful tool. It provides block-level deduplication, compression, and thin provisioning. So 3 things in one. In an advertisement, you can say, buy one, get 3 features. And you don't have to buy it, it's in the kernel. You can see it on the right side. It's an image by Red Hat, how it is implemented in the storage stack. Most of the time, it is used in virtualized environments. So you have multiple virtual machines, for example, running on the KVM hypervisor. And here you have often the situation that you have the same data. So there's a good use case for deduplication. Often you can use compressed data, and you also want to have thin provisioning in there. So the VDO targets, the target does support all 3 functions here. And as it is in the device mapper target, it can add these features compatible with any file system. We mentioned that the device mapper is in the middle of the storage stack, and it doesn't care which file system you put upon it. So it can be used very flexible. One thing you have to keep in mind is that VDO does not protect against data corruption itself. So you're relying on the integrity protection of the storage stack below it. So you can stack it with other devices or use hardware that supports that. To use it, it's strongly recommended that you use LVM. It's also in the documentation on there. And originally, this kind of software was not open source software, but it was developed by a company called Permabit, which has been purchased by Reddit in 2017. And Reddit took the code, integrated it into the mainline kernel, and now it's mainline since kernel 6.9. And for me, that's a very good example how open source can work, also in cases where parts of the software is developed in a proprietary system. There are many use cases or examples where companies like Reddit buy the company and make it open source and available for the whole world. And yeah, that's really one of those growth advantages we see in open source, which we don't have in proprietary software. To show a few details of these functions, the data application, VDO managed an assignment of the logical block devices to the physical ones. And after data application, several block devices can be mapped to the same physical block address, by that reducing the space necessary on the physical device. And these are referred to as shared blocks. If a shared block is overwritten, it just allocates a new physical block to store the new data. So as simple as this. For the compression, it uses the LZ4 algorithm to provide a lossless data compression for further data reduction. If possible, it compresses it in a way that several blocks fit into a single 4K block on the underlying storage space, because this is the block size which is most often being used. And this LZ4 algorithm provides a good compromise between speed and compression ratio. So although it hasn't that good compression ratio than the LZO algorithm has, it's faster for compression and decompression speed, and it's also being used for OpenZFS or SquashFS, so it's a good example to use here to get a good balance between speed and compression ratio. How is that achieved? How is VDO using this internally or organizing it? To organize the data, VDO is using so-called slabs. This is the physical storage divided into different kind of pieces. And each slab is a continuous region of storage. Minimum, our default size is 2 GB, minimum size is 128 MB. It can go up to 32 GB. And a single volume can have up to 8,000 slabs, so up to 16 TB for the 2 GB slabs, for example, or 256 TB for the maximum of 32 GB slabs. Important information regarding the data usage: the VDO target always reserves at least one entire slab for metadata. So it's not a thing you're using on your laptop, it's a thing you're using in the server environment, because otherwise on the laptop you wouldn't take an advantage of the usage. And the slab size has no effect on the performance. That's also important to know. How does the deduplication work? It's using a so-called universal duplication service, and it was developed to efficiently identify duplicate data. And they did imperial observations. So they found out that most data sets with significant amount of duplicate data are found in data that has a temporal locality, so that are about the same time being written. And new data is more likely to duplicate recent data than it is to duplicate old data in general. So they focused on this kind of observations to not spend too much effort in finding every duplicate in there. So it doesn't find each duplicate in the data, but it uses, again, a way that's a good thing between performance and efficiency regarding to the storage space. For this, the VDO volume reserves at least 3 GB of space for metadata or more. So you really have to check the space saved by deduplication and compression so that it do not canceling it out by your metadata requirements. And for that, there is also a tool provided, the video estimator, where you can put in your numbers and see, okay, will I get an advantage out of here or not? Yeah, placement in the stack. It performs, as mentioned, deduplication, compression, and thin provisioning. And these functions are automatically used for all layers that are based on video. And for that reason, to avoid negative effects, you have to take care where to put it in the stack. You can stack multiple device mapper targets over each other. But to don't get negative effects, you should, for example, dm-crypt or software it only use below video, because it wouldn't make sense to use it above. When you're encrypting data, the same data twice with different keys, you get different data, and when you put it on top on video, it cannot find the deduplication things in here. So you have to be careful where to place it, and when you place it in the right way, you can really take an advantage out of it. And there's really great documentation at the Red Hat site for that, so check it out to get more information in there. And in case you're using virtualization, KVM setups, take a look at it. It's in the kernel since 6.9, so rather recent. Short example, which follows here. I'll do a LV create with the type video target for the video target, and getting one here, the video test target, as you can see in the middle of the slide. And when I write data on it and copy it, I did a simple file creation of random data in a test file, copied the test file multiple times, and you can see then with the video stats command how much space you are saving. And yeah, this shows it that you can really take advantage of it in those environments. Yeah, one or two are left for the production use. Write cache caches writes on a persistent memory or SSD, doesn't cache reads. Maybe there's soon another one, DMP cache, and it's in discussion yet. It could be in 6.18 maybe. There are 2 articles on that here too, so watch out for this if you want to use a caching solution. There will be new ones in the future. And then the last one, the dm-zoned device, which exposes a zoned block device, like a shingle disk, as a regular block device without any write pattern constraints. There's also more documentation on there. And yeah, so there are 7 minutes left. I'll finish with the targets for debugging use to get in time for lunch. There are multiple of them. I think there are 5. They are mainly used for development and debugging. Example, the delay target. This delays reads and or writes and or flushes. Next one is dm-dast, which is interesting for file system developers because it emulates the behavior of bad sectors at arbitrary locations. It behaves similar to the linear target, but at any given time you can send a message to that target to start failing read requests on specific blocks. So this is the example where you can send a message with a dm-setup command to a target, yeah, when you have this enabled, reads of blocks and the bad block lists will fail with an I/O error. So when you do a write on the other side, it will result in removing the block from the bad block list and successfully completing the write. By that, it emulates the remapping sector behavior of drives with bad sectors, and you can use it for testing your file system. dm error, there's simply errors. Any I/O that goes into this area also useful for testing or created devices with holes in them to ensure that you're getting an error when you use that. Simple example here, just created a target like this, did some I/O on that, get an I/O error, no data is being transferred, and I also get it on the console, as you see down below here. So it works as expected, and just to show you another example of how the dm-setup command is working. Yeah, and the last two, I think, dm-flaky is same as the linear target, except that it exhibits unreliability behavior periodically, also for simulating failure of devices. And you can combine it, for example, with a delay target. You can stack them over each other. And last one, dm0, provides a block device that always returns 0 data on reads and silently drop writes, similar to def0, but as a block device. Also used for tests, but this can also be useful for recovering linear and weight type targets when you combine it with the snapshot target, so you can also use it for some, not only debugging, but also some pre-production use case. And with that, 4 minutes before the time is over, I think we did it. We did this short recapitulation, went through the storage stacks, shown some dm-setup comments, and I hope I had the possibility to give us some input for the targets for production use and debugging use. And at that point in time, I want to thank the kernel developers who did all of this stuff, or all of the layers they put into it. And also the ones who helped me to create this diagram here. There are many of those. In the first time it was Hannes Reinecke and Christoph Hellwig, and recently, the last years, also Richard Weinberger, who is also, I think, in the audience back then. Yeah, okay, thank you. So thank you for them, and on this point I want to give a big round of applause to the kernel developers. Without them, we wouldn't have this in the kernel. So thank you for doing this and making open source great. Thanks. So 3 minutes. Are there any questions?
Yeah, you mentioned that you could use the dm0 device for recovery with snapshots.
Yeah.
Can you explain?
I think maybe we can talk about this. The question is how to use the dm0 target with snapshots for recovery. I think we can talk to in the break in the 2 minutes. I think it's those two. Yeah.
I want to suggest maybe
Yeah.
update the slides for the next talk.
Okay.
For dm-logwrite, to add that to debugging, because it's pretty useful. I've written some tests with it.
dm-logwrite.
Logwrite, yeah.
Okay.
Like when you record the operations and you can take snapshots and replay. So
Okay.
then you can reproduce certain failure.
Okay, the information is that with dm-logwrite, you can reproduce certain failure scenarios by recording them before to add this in the slides. And thank you for the suggestion here. And I ask you if you could chat a little bit more in the break, because I think I've overlooked that. So thank you for that. So any other questions? Yeah, one other question. Yeah, the question is, what happens with VDO when a new kernel is released? And as we heard in the last talk before, the kernel developers focus on not breaking user space in any case. So they ensure that it's compatible still, so you can use it like any other target. Maybe there will be some features added, but it will never break what you already have in place. You don't have to be scared that the data is being lost anywhere at this kind of point. So, but it's a good question, and it's a good reason to stay with open source. You don't have the situations that something gets stopped and you have to move, like in October many users are doing with proprietary systems, and hopefully they're switching to Linux here. Maybe, yeah. So I think to ensure that everybody of you is getting lunch, and the seconds are already counting down in red color here, I'll say, well, let's go for lunch. And for those of you who want to grab a copy of this diagram, 50 copies here, so you can get yours here in front. Thank you for listening and enjoy the conference.